Hello everyone, Mrs. Hanson once again. We're on about page 8 of our notepad on chapter 4. We've been hinting around at this molecular geometry, molecular shapes of molecules, all through the pathway of drawing Lewis dot structures. We're finally catching up some notepad opportunity to some practice we've been sprinkling in all along. So we know that Lewis structures, they're really good at giving us information about how atoms are connected, but it really doesn't give us a good idea of how the molecules are shaped in a three-dimensional geometry. So to determine the shape around a given atom, we look at a central atom and determine how many groups surround the atom. So if we have a central atom, usually it's a carbon, let's just say as an example, and carbon we know have 4 bonds. What are those 4 bonds leading to? Alrighty, so the group surrounding the central atom. Now, as we decide whether an atom is bonded to all other atoms, that's an important decision. Or sometimes the central atom is bonded to atoms and lone pairs of electrons. So we need to consider both. When determining the molecular geometry around a central atom, we look to see what it's attached to. The attachments are bonds leading to atoms, or they are unbonded lone pairs. We use the Vesper Theory, which stands for the valence, shell, those are the outermost electrons, aren't they? The valence shell electron pair repulsion theory. And really what this tells us is we want to maximize the space around the central atom and give as much room to each attached atom, and especially room for each lone pair of electrons. So the most stable arrangement keeps the groups from the central atom leading all out, these groups that are attached. We want to keep them away from each other as far as we possibly can. And that's the goal as we start to consider molecular geometry using the Vesper theory. So let's consider an atom that is only bonded to 2 groups. Any atom surrounded by only 2 groups is known as a linear molecular geometry, and it has a bond angle of 180 degrees. As an example of a linear molecule, we can represent that with carbon dioxide. You notice that carbon who needs 4 bonds. We could start by saying 1, 2, 3, 4. We hook an oxygen, 1, 2, 3, 4, 5, 6. There's a shared pair. 1, 2, 3, 4, 5, 6. There's a shared pair. And we can see how we have a resulting double bond form when we hook together all electrons to create an octet for each atom. Carbon has its required 4 bonds. They're leading to oxygens who have 2 bonds and 2 sets of dots. If you remember, that's the requirement. Oxygen, 2 bonds, 2 sets of dots, perfect. Oxygen, 2 bonds, 2 sets of dots, perfect. And in the carbon, all 4 bonds. So everyone's octet is satisfied when we have 2 double bonds leading from the central atom carbon. We have a set of double bonds heading out in each direction. So we have 2 groups attached to the central atom. You see how this right here has 2 groups. One of the groups is an oxygen atom, and the second of the 2 groups is another oxygen atom. Notice there are 0 lone pairs. So all we're looking at is standing at the carbon atom. I look one way and I see an oxygen. I look the other way and I see an oxygen. That creates a very linear molecule. Bond angle 180 degrees from one oxygen to the next, a very straight line. If we have a central atom that is surrounded by 3 groups and no lone pairs. So let's say 3 groups. I'm going to just kind of make that easier. You're leading to 3 different atoms. Maybe you like that word better than the term group. It might be more meaningful. From the central atom, I'm attached to 3 atoms and 0 lone pair of electrons, right? So I'm standing in the center, and all I do is I can look up, I look down, I look this direction, and all I see are atoms, no lone pairs. And this, as an example, is trigonal planar. It lies flat on the table, and it looks just like an equilateral triangle. Notice that the equilateral triangle has the same distance between all of those outer atoms, exactly 120 degrees. As an example, you might have a carbon attached to 2 hydrogen, leading up to a double bond, oxygen. Now remember, it doesn't matter that it's a double bond, it still leads to 3 atoms and 0 lone pairs. So when we say groups or atoms, a single bond, double bond, triple bond, it doesn't matter. I'm leading to 1, 2, 3 atoms, and there's no lone pairs around that carbon. Carbon has the 4 bonds that it would like to have. You know, as a second example, we could draw boron trifluoride. We did that one a moment ago earlier in the notes. We said boron lives in group 3A, and so it's one of those exceptions to the octet rule. Does that sound familiar? Since boron lives in group 3A, it has 3 valence electrons. Well, of course, the fluorines have 7 valence electrons, and so when they form their single bonds, you can see that the boron will lead out to all fluorines equally in all directions, forming single bonds along the way. Boron trifluoride, boron, the central atom, attached to 3 atoms. All of them are fluorines here. And of course, we see that there are 0 lone pairs of electrons. So this would be a trigonal planar molecular geometry. Boron sits in the middle. Just as an equilateral triangle, we separate, that was supposed to be a fluorine. We separate all of those by 120 degrees around those fluorines. Great. Well, let's keep exploring. Now let's suppose our main atom, the central atom, has 4 groups around, 4 attachments. For example, let's say we have an atom in the center, and it has attached to 4 groups. And when I say groups, just think of it as atoms. It has, from the central atom, I can count 4 atoms it's attached to and no lone pair electrons, so 0. I look in all directions and I see atoms. And now we're noticing that we get this little feel of a 3-dimensional when we start seeing this dash wedge scenario. The dash is coming behind the page and the wedge is coming out of the page. This is what we call a tetrahedral molecular geometry. Methane is an example of a tetrahedral molecule. We place carbon in the center. In the same plane as the carbon, leading directly up, is a hydrogen. In the same plane as the carbon, coming down would be a hydrogen. Coming out of the page, that's this wedge, is another hydrogen. And here going behind the page is the 4th hydrogen using a dash. So this is giving us an idea that there's 3 dimensions, and the ball and stick model here really does a nice job. And you can see that there would be 109.5 degrees in all 4 corners of a tetrahedron. So the bonds are in the same plane. We use a solid line. If they're coming out of the page, you see that as a wedge, and they're coming behind the page. You know, you can't see it, it's behind the carbon, if you will. That's used a dashed line. A tetrahedral, 109.5 in all directions. When the central atom is attached to 4 atoms and no lone pairs, the geometry becomes a tetrahedral shape. Suppose the central atom has 3 atoms it's bonded to and 1 lone pair. For example, nitrogen, I know nitrogen lives in group 5A, so it has 5 valence electrons. We've realized that nitrogen wants to have 3 bonds and 1 set of dots. When I draw the Lewis dot structure for ammonia, NH3, the Lewis dot structure might make us think that it's a nice 90-degree angle between these hydrogens, but we understand now that the Lewis dot symbol, although it's great for showing connectivity and what's attached and how it's attached, the Vesper theory gives us even more information about the true three-dimensional shape of this molecule in space. So the nitrogen now, the nitrogen in the central atom is attached to 3 other atoms, and it has 1 lone pair of electrons on top of it. See them? So I count 1, 2, 3 atoms, and also I have a set of dots. So the Vesper theory now says, instead of tetrahedral where all 4 attachments led to atoms, we've got a different structure, right? We've just chopped off the top of the pyramid, if you will. Now it's called trigonal pyramidal. Trigonal pyramidal is how you say that. So notice the base of a pyramid, those hydrogens coming down and all are sitting on the top of, sitting on the surface of the table. Those are all flat on the table, and then this nitrogen is just set up high. Now remember, there's a set of electrons here, right? And so these electrons actually take up space. And the reason we see a little decrease in bond angle is because the electrons are much more sizable than an atom would be, and therefore forces these 2 hydrogens to be just a little bit closer together. Let me repeat that. The hydrogen, when we had all of the attached, whoops, I'd make that a dash. Remember on the previous slide where I said we had 4 bonded atoms and 0 lone pair? We called that a tetrahedral. The ideal bond angle was 109.5 degrees. But now all of a sudden, we've taken off one of the 4 attachments, and we have these big electron cloud up here, and it's going to smush these guys just a little bit closer together. So instead of the ideal 109.5, it's just a little bit smaller, 107 degrees between those hydrogen atoms. Let's suppose our central atom is attached to 2 other atoms and has 2 sets of lone pair electron, 2 sets of dots, if you will. So now all of a sudden, of the 4 domains, 2 are bonded to atoms and 2 are lone pairs. What this is known as is the molecular geometry of bent. And remember, each time we take off an atom and add another set of electrons, the atoms get just a little more smushed together. So let's consider water. The central atom of oxygen. Notice these big electron clouds up here. Water is a bent molecule. H leads up to O, leads back down to H. And this right now is approximately 105 degrees in the bond angle. Remember, 2 sets of electron pairs are going to take up even more space, forcing these hydrogens to be just a little bit closer. The ideal bond angle of 109.5 is when we had 4 atoms and 0 lone pair. Then we said, what if we took off 1 atom and had just 1 lone pair? Then it went to about 107 degrees. And then if we took off a next atom and we had 105 degrees when we had 2 atoms and 2 lone pair. All of these are 4 domains around the central atom. Domains means how many atoms and how many lone pairs. If all 4 domains lead to atoms, 109.5 is the bond angle. Of the 4 domains, if only 3 lead to atoms and 1 is a set of lone pair electrons, it reduces the bond angle slightly to 107 degrees. And of the 4 domains, if only 2 lead to atoms and we have 2 lone pair electrons, then we've reduced the bond angle slightly more to be 105 approximately. So a little bit less each time we take off an atom and leave a set of lone pairs. These are the molecular shapes that you need to work to remember based on the number of atoms and lone pairs around the central atom. We said, as an example, if we had a linear molecule leads to just 2 other atoms. The electron domain, total number of groups is 2. If you like that term, this is what I used to call it when I was a student, electron domains. How many things are around the central atom? That's a domain. If there are 2 and all are bonded to atoms, it's linear. If there are 3 domains and all 3 lead to atoms, 330 is your Vesper count, and that's trigonal planar with a 120-degree bond angle. If we have 4 domains and all 4 lead to atoms and 0 lead to non-bonding pairs, then it's called tetrahedral with 109.5. If we have 4 domains and only 3 lead to atoms and 1 lone pair, like ammonia, we said that was about 107 degrees. And if 422 is your Vesper count, it's even less at about 105 degrees. This is a great chart from your text. It's what you want to work to memorize to understand the molecular geometry. And let's practice. Let's practice in just determining the shape. Now remember, when we're asked to determine the shape, you have to select one central atom at a time. So I'm just reminding you that we can only examine one central atom. So for instance, I'm going to put an arrow on that carbon. Now let's examine its molecular geometry. I notice that this carbon is attached to 2 other atoms. It does not matter if it's a single bond one direction and a triple the other way, that is still considered 2 domains. It's attached to 2 atoms, and there are 0 lone pairs on that. And now we know with the Vesper count of 220 that is a linear molecule. The same is true for this other carbon as well. They are identical with the Vesper count of 220. When I look at this guy, the central atom nitrogen, the nitrogen has 4 domains. Remember, I'm defining domain as either an atom or an electron pair. Right? So a lone pair, if you will. That's what a domain means. There are 4 domains in this particular example of the ammonium ion, our polyatomic ion of ammonium with its NH4 plus molecular formula. Of the 4 domains, 4 are bonded and 0 are unbonded or lone pairs. And so your Vesper chart becomes your count 440. And remember, you're working to memorize 440. Oh, that's tetrahedral with bond angles of 109.5. Great. This just takes repetition. It's really not hard, but there's some fundamental skills we need to practice. For instance, letter A says, what's the central geometry around sulfur? And they did not give me the Lewis dot structure first. So it's like I got to draw it first and then decide. All right, so when I find sulfur, I can see it's in group 6A. That tells me sulfur will have 6 valence electrons. Each hydrogen that's around it will contribute 1, but there's 2 of those hydrogens, so we get 8 electrons. Sulfur connecting back to hydrogen, that used up 4 of those electrons, leaving me 4 again. So there I fill the dots. So this is probably very easy Sulfur is in group 6A, so 6 valence electrons, 2 bonds, 2 sets of dots, like oxygen. Now this is how I drew it in terms of its Lewis dot structure, but it's not what it looks like in space, right? It's not truly its molecular geometry. Around the sulfur atom, we have 4 domains, 4 things. Remember, the term domain means atoms or electron dots, right? Of those 4 domains, 2 lead to atoms, 2 lead to lone pairs. So just to emphasize, a domain. Here's 1, 2, 3, 4 domains. Of those 4, 2 are atoms, 2 are lone pairs. So your Vesper count is 4, 2, 2. When you use your Vesper chart that you're working to memorize, 4, 2, 2 is a bent geometry with bond angles of about 105. So sulfur to hydrogen drawn correctly would have a bent molecular geometry. How about letter B? We're looking at carbon as the central atom. Carbon, of course, lives in group 4A. And so we know that carbon is going to have 4 valence electrons. Alrighty. Hydrogen each contributes 1, so a total of 2. And chlorine, we know, lives in group 7A. And so there will be a total of 7 times 2 is 14. But you're getting the idea, I'm sure, that carbon with its 4 valence electrons, 2 of those will lead to hydrogens, and the other 2 will lead to the chlorines who have 7 valence electrons, form a single bond here, form a single bond here. So this is its Lewis structure. However, we know that's not what it looks like. In space, its 3-dimensional geometry is not flat with 90-degree angles. Around the central atom carbon, there are 4 domains, 4 atoms. So all 4 of those lead to atoms. It didn't come out very neat. There we go. And 0 lone pair. So on your Vesper chart, you're looking for a Vesper count of 400. When I go to 400, you're looking at tetrahedral with bond angles of 109.5. So to draw that better, you'd have carbon leading up to a chlorine in the same plane. You'd have hydrogen in the same plane. You'd have a chlorine coming out as a wedge coming out of the page and a hydrogen going behind. And your bond angles here, 109.5, tetrahedral. This bond angle would be about 105 if I go back and add that for letter A. Well, how about letter C? NCl3. I need a little more space. NCl3. Nitrogen lives in group 5A, so 5 valence electrons. Chlorine lives in group 7, so it has 7 valence electrons, so there'll be 21 dots, 26 dots by the time you're done. These are very simplistic drawings. Nitrogen leading out to 3 chlorine. That used up 6 valence electrons there, 6 to create 3 bonds. Fill the outer atom's octet next. That used up, I forgot the 2, that used up 6, 12, 18 dots, leaving 2 remaining to complete the octet on the nitrogen. This is the Lewis dot structure for NCl3. But it's not what it truly looks like in space. So that's where we're challenging ourselves to now develop a better view of what it really looks like. It's not 90 degrees lying flat on a plane. Around the central atom, what do you see? I see 4 domains. four things, four objects, if you will. Lone pairs and bonds are domains. Of those four domains, three of them lead to atoms, and one of them leads to a lone pair of electron. So your Vesper count is 4, 3, 1. 4, 3, 1, that's our trigonal pyramidal shape. Bond angles of about 107 degrees. So the nitrogen in the center, with its pair of electrons, and leading down would be a chlorine. Coming out of the page would be the next chlorine. And going behind the page would be the third chlorine. And these bond angles are approximately 107 degrees. There's one more, isn't there? CH2 double bonded to CH2. So we have C double bonded to C, and then I see an H for each of these. So that's kind of the structure as I put together two hydrogens connected to a carbon, double bonded to one another. Now I did that on purpose because that's not what the molecule looks like. Let's focus on only one carbon at a time, knowing we'll get the same answer no matter which carbon I choose to look at first. That carbon has three domains. Now remember, a domain is a bond. It doesn't matter if it's a single or a double or even a triple bond. A bond is a domain. And so I have 1, 2, 3 domains. Let me count that again with a highlighter. I have 1, 2, 3 domains on that carbon, and all three of them leads to atoms. So on your Vesper chart, you're looking at a 3, 3, 0 Vesper count. 3, 3, 0. Oh, that's trigonal planar. Well, that's not what I drew. So let me redraw that and kind of emphasize what it truly looks like. The carbon double bonded to carbon, perfect. But now remember, these hydrogens are coming out to make a trigonal planar 120 degree bond angles right here. Same over on this side, it's the same answer. So the carbon to carbon double bond leads out to these hydrogens in a trigonal planar molecular geometry. On both carbons, they're identical, trigonal planar. Let's keep practicing. Which model represents NH2 negative amide? So we have a choice. If this is the nitrogen, does it lead out to have 180 degrees as the bond angle to each hydrogen? Or is this the nitrogen leading down to the hydrogens? What would be correct? Well, remember, nitrogen lives in group 5A, so 5 valence electrons. Hydrogen lives in group 1A, and there's 2 of them in that formula. And there's a -1 charge, meaning we get an extra electron when we build. So 5, 6, 7, there's 8 electrons to build our molecule with. So we'll say nitrogen in the center, and it's going to lead out to both hydrogens. We used up 4 electrons to make 2 single bonds. Hydrogen doesn't want any dots, so all remaining dots have to go on the nitrogen in the center to use it up. So notice this guy in the center, the nitrogen, has 4 domains. A domain is a bond leading to an atom or a set of lone pair. Well, of this central atom, I can count 1, 2 lone pairs and 2 atoms. So when I'm considering of the 4 domains, 2 atoms, 2 lone pairs. So your Vesper count is 4, 2, 2. Remember what that is yet? 4, 2, 2 is a bent structure. So when I look at my structure, 4, 2, 2, nitrogen with 2 lone pairs leading down to hydrogens is a bent molecular geometry with about a 105-degree bond angle between the 2 hydrogens. And clearly we see it's not linear. It would only be linear with a 2-2-0 Vesper count. This was a 4-2-2 Vesper count. And that's how we determined letter B was the correct structure, just by drawing out the Lewis dot structure. Sometimes we're looking at these shapes of molecules and trying to decide what would the octet be given and the shape around each of the indicated atoms. So add all the lone pairs and then tell me the shape of where you're seeing the arrow point to. Alrighty. So I know that carbon lives in group 4A. Carbon needs 4 bonds. Oxygen lives in group 6A. That's 2 sets of bonds, 2 sets of dots. Nitrogen lives in group 5A. So when we look at that 5, we can see that it wants 3 bonds and 1 set of dots. You know what I mean by dots, which are lone pair. I guess dot sounds funny. There we go. So that's just a reminder of how we know things attach. Carbon is in group 4A, so it needs 4 bonds because it has just 4 valence electrons. Oxygen lives in group 6A, so it wants to have 8, so it's going to gain 2 more. Nitrogen, of course, lives in group 5A, so that's how we're predicting how many set of dots, how many bonds. So carbon, in our letter A here, carbon has the 4 bonds that it wants, so it will not be receiving any dots. He's good. The oxygen, well, it has the 2 bonds, but clearly we see it also needs 2 sets of dots to complete its octet. Alrighty, so we have 2 bonds, 2 dots around the oxygen. Now that I've got all the dots placed, we can go in and decide the Vesper count. Let's do the carbon first. Around the carbon, I see 4 domains. And when I'm referring to domains, I simply mean either atoms or lone pairs. So those 4 domains for carbon all lead to atoms and 0 lone pairs. So do you see on the Vesper count, it would be 440. And that, of course, we're learning is tetrahedral, 440. Now let's focus on the oxygen because it also has an arrow pointed at it. The oxygen next. Notice that, let me just erase. Notice that carbon, which had all atoms, oxygen looks a little different, right? Not only do we see the 2 sets of atoms, but when we had these highlighted with there, when I see that they have also 2 sets of dots. So this is a little different. Oxygen does have 4 domains, domains being atoms and lone pairs. 2 of them lead to atoms and 2 lead to unbonded lone pairs. So this Vesper count is 422. And we're working, it's coming. You know that needs to be called bent. So at this particular part of the molecule, the oxygen is bent. So think about what that really looks like. Here's the hydrogen. Matter of fact, I'm going to put the 2 in the same plane. I'm going to go like this in the same plane. That means that this hydrogen kind of completes like this over here, giving it that tetrahedral geometry. And then oxygen, of course, would lead next, and hydrogen comes out. And that's the bent part of the molecule. So that gives you a better visual of what it really looks like. 440 around the carbon, 422 around the oxygen. That's a bent part of the molecule around the oxygen, tetrahedral around the carbon. How about letter B? we're pointing at the N in NF3. I really do think we just drew that a moment ago. So we're learning that this is going to be kind of the setup around NF3, where we have 4 electron domains. Of the 4, 3 lead to atoms, and 1 leads to a lone pair. So our Vesper count is 431. We're learning repetition, right? 431. This is called trigonal pyramidal. And that trigonal pyramidal gives us about 107 for the bond angles. And letter C, you know, I don't see a single spot that needs any electron dots. All the carbons have 4 bonds, and all of the hydrogens are all set with single bonds, so there are no lone electrons. So let's just highlight this carbon first and examine how many attachments it has. Notice it has 1, 2, 3, 4. The yellow carbon that's highlighted is leading to 4 atoms. So of the 4 domains, 4 lead to atoms, and we have 0 lone pair. So that carbon is tetrahedral. Right here, tetrahedral. Well, let me clear that ink and let's focus on the next carbon where I see the other arrow, and let me highlight that one bright pink. Let's examine him next. How many things is it leading to? Well, I count 1, 2, 3 domains. There are no lone pairs, but only 3 domains. So of those 3, they all lead to atoms and 0 lone pairs. So your Vesper count is 330, which we know to be trigonal planar. 330 trigonal planar, 440 tetrahedral. You're doing good work. Here we have an example where we're trying to match the molecular shapes of the compound. So letter A, just so you can see that it has a 180-degree bond angle, we would call this linear. And letter B is giving us a bent molecular shape, just to kind of see what that would look like. Bent of about, what was that, 105-degree bond angle. So this story problem is asking, when I look at a compound's formula, BeCl2, OF2, SCl2, notice these all are composed of 3 atoms. Around the central atom, how do the other 2 attach themselves? And that answer lies in drawing the Lewis dot structure and deciding how many valence electrons, you know, how many dots does it have compared to atoms. So let's draw the Lewis dots and decide, will it have a bent is 422 on the Vesper count, or linear is 220 on the Vesper count. Let's model. Let's do the first one, letter A, beryllium chloride. Beryllium lives in group 2A. Do you see it there with the elemental symbol Be? That tells me it only has 2 valence electrons. So there's its starting structure. And clearly I can see when I add the chlorine to create single bonds with its 7, that this molecule satisfies the octet rule for each, knowing that since this is group 2A, it will be an octet rule breaker. It doesn't want any more than 2 single bonds. So its Vesper count is indeed 220, so it will be a linear molecule. It'll look like letter A. But when we look at OF2, which would be called oxygen difluoride. This is letter B, oxygen difluoride. You see oxygen with its 6 valence electrons. Oxygen lives in group 6A, so it's starting with 6 sets of electrons, and when I attach it to the fluorines, and knowing fluorine has 7 of its own, we end up with a Vesper count of 4, 2, 2. So it really looks like this, a bent molecule. So this structure ends up to be bent because the oxygen has 2 sets of dots in addition to 2 sets of atoms. The other one we were given SCl2, and friends, that's going to be identical to OF2. Oxygen and sulfur live in the same family, don't they? They both have 6 valence electrons. So when I draw sulfur, it will also have 6 valence electrons, giving me 2 bonds, 2 sets of dots. And this structure ends up to be just like OF2, where it's a bent molecular geometry. Can you think of an example of a molecule that looks like this? Well, I included this to kind of look at, what is the difference in shape? I noticed that I have a central atom. Here's what's in common, right? And a central atom leads to 3 atoms. Right, so if I were to call this just element A, and I'll call this element B, this formula would be A, B, taken 3 times there, right? They have the same molecular formula, right? The central atom has 3 attachments, and yet their geometry is very, very different. When you look at your Vesper chart, when I have one central atom that's leading out to 3 other atoms, and they're looking like an equilateral triangle, we called that trigonal planar. That's 3, 3, 0. That's an example, BF3. So 3, 3, 0 is this Vesper count, knowing that it's trigonal planar. And we can say, well, that's an example. I could do boron trifluoride and have a count of 3, 3, 0. And notice I'm making an equilateral triangle. 120 degrees is our bond angle there. But when you examine your Vesper chart and you find this particular shape, where we have one central atom leading down to the 3 other atoms, and you have a set of electrons up here. You see that? That the Vesper count is 4, 3, 1 to give us this trigonal pyramidal shape. That was our example right there, ammonia. So when I saw this example, I saw that this would have a Vesper count of 4, 3, 1 called trigonal pyramidal. And that the central atom must have a pair of electrons on it as well. Leading down would be a hydrogen, leading out also a hydrogen, and leading back also a hydrogen. That's called trigonal pyramidal. This is a molecule we know by a common name called ammonia, NH3. This is a molecule we'd call boron trifluoride. Doing good. You're doing really good. Why don't you just take a moment, work ahead of me? We have a few more examples. Work ahead of me, think real hard, and come back when ready, and we'll do our checking. Okay, are you back? Well, here I'm looking at just finding bond angles, and bond angles really are going by the central atom. So even though I actually see 2 separate arrows here, they're going to be the same answer. So when I think about the carbon, that's our central atom. I can see it has 4 domains. And if that's still confusing to you, let me highlight them. It's leading to 1, 2, 3, 4 things. Domains can be atoms or lone pairs. So of the 4 domains, all are leading to atoms, 0 are lone pairs. So your Vesper count 440 is tetrahedral. And therefore we know that the bond angles are going to be 109.5. Let's look at this central atom, carbon. The carbon here has 2 domains. The central atom is leading out to 2 other atoms. So this Vesper count is 220, which is linear, which is exactly 180 degrees. Let's examine this particular carbon next. Oh, I should make that a different color. Let's make it bright yellow. How many things is it attached to? Well, 1, 2, 3, 4 attachments. So that means this carbon has a Vesper count of 440, which means it's tetrahedral, which means that bond angle is 109.5 degrees. Let's one more to examine, and that's the oxygen. The oxygen has 2 sets of dots, 2 bonds. Did you remember that? Oxygen requires dots. So this Vesper count here on the oxygen is 422. Of the 4 domains, 2 lead to atoms and 2 lead to lone pairs. 422 is a bent molecular geometry which has bond angles of about 105 degrees. These are kind of fun, right? Let's redraw. We have some bigger space to work. Here's letter C. I'm just going to redraw it so I don't keep tripping over my workspace. Now remember that oxygen has some dots, and if that, I could just tell that's upsetting, so I just put on the dots to make it look right. So the first one we want to look at is right here. Now I'm tempted to say, well, golly, that looks like a straight line. I'm going to call it 180 degrees. Don't do it. Don't fall for that mistake. This central atom carbon is attached to 1, 2, 3 domains. That's the step you cannot miss. 3 domains. Of those 3, all 3 lead to atoms, and 0 lead to lone pair electrons. So your Vesper count is 330. Do you remember it by heart yet? Trigonal planar. Trigonal planar 330. So when you're considering that, don't just let that Lewis dot structure fool you. We got to go all the way to draw and then find 330. That's called trigonal planar. So this is actually 120 degrees. I know it doesn't look like that, but it's not drawn in the spatial correct orientation. Let's consider now this next bond arrow, which is going from here to here. That means we have to examine, let me make it bright pink. We're going to examine this carbon, and I can see that it has 2 domains. So that carbon, this guy here, is 4, oh, it's not. It's 2 domains. I just said it and wrote 4. 2 domains. Both of those lead to atoms. 0 are lone pairs. So you have a Vesper count of 220, which we understand is linear. So this molecule there is indeed 180 degrees. And the last one you would see here is the same as up above, 120 degrees. So if you just examine what it really should look like, the hydrogen, they come off at bond angles of 120 degrees. Then this carbon leads to an oxygen that is indeed 180 degrees. Alrighty. Good. All right, you're doing good work. What's next? Well, draw carbon tetrachloride All right, that's easy. Carbon with 4 chlorines attached to it. We know that it's going to be tetrahedral. 440. We're getting so good at it, we'll just go straight to the molecular geometry. Carbon requires 4 bonds, so I can see that it will be tetrahedral. Now let's draw C2Cl4. Well, those carbons are going to hook together, carbon to carbon, and then think symmetry. We have chlorines coming out of each. And then, of course, this would have to be a double bond to create the octet that carbon requires. I'm filling in the dot requirement for the chlorines. And now you can see that each of those carbons would have a Vesper of 3, 3, 0, trigonal, planar. You've done a ton of good work with the Vesper theory. We've spent 50 minutes on that. I'm going to pause the video here, give you time to process, digest, go do some homework practice on your Connect. We have one more lesson on polarity and electronegativity. Come on back soon when ready.